All right, let's jump right into this explainer. Today, we're looking closely at the actual mechanics of how parallel wires interact magnetically. When you see two separate conductors spontaneously pulling towards each other or pushing apart in thin air, it's this brilliant, almost magical display of pure physics. But it's totally predictable, and it governs absolutely everything, from the simple circuits on your desk to the massive power grids outside your window.
Here's our roadmap for today. We'll hit the rule of attraction, the force formula, standard force calculation, finding total force, and finally, finding equilibrium distance. Let's get to it.
Section 1. The rule of attraction.
So it all boils down to a super simple binary rule. When your currents are flowing in the exact same direction, those conductors are going to attract each other. But flip one around so they're flowing in opposite directions, they repel. It's really that straightforward. Keep this foundational rule in your back pocket because it acts as the ultimate reality check for all the calculations we're about to do.
Section 2. The force formula. Before we just throw a giant equation at you, let's isolate our heavy hitter here, μ0, better known as the permeability of free space. This constant is locked in at exactly 4 pi times 10 to the negative 7 Tesla meters per ampere. Getting this out of the way right off the bat makes the core calculation a whole lot less intimidating.
Now for the rest of our ingredients, we've got F over L, which is our force per unit length, measured in newtons per meter. I1 and I2 are simply the currents we're dealing with, in amps. And D, that's just the physical separation distance between our wires, measured in meters.
Put all that together, and boom, we have our master key. To find the force per unit length between any two parallel conductors, the formula is F over L equals μ0 times I1 times I2, all divided by 2 pi d. This one little equation is exactly how we crack these physical systems wide open.
Section 3. Standard force calculation.
Let's actually put this to work. Picture two long, straight, parallel wires suspended in the air. Let's say one's carrying 5 amps, the other's carrying 10 amps. They are flowing in the same direction, and they're separated by a gap of 10 centimeters. We just grab our formula, drop in our constant, plug in those currents, and quickly swap that 10 centimeters into 0.1 meters just to keep our units clean. Then we simplify.
And there we go, we get a magnitude of 1 times 10 to the negative 4 newtons per meter. And remember our golden rule from a minute ago? Since both currents are flowing the same way, we know immediately what kind of force this is. These wires are absolutely attracting. They are physically pulling towards each other.
Moving on to Section 4, finding total force.
Let's step things up a bit. Imagine two wires, both exactly 2 meters long, with just a tiny 5 millimeter gap between them. This time, they're carrying equal 20 amp currents, but in opposite directions. First up, we find the force per unit length, plugging in our 20 amps and that 0.005 meter distance, which spits out 0.016 newtons per meter. But we want the total overall force across the whole length of the conductors, so we simply take that rate and multiply it by our 2 meter length.
That gives us a grand total of 0.032 newtons. Now look at those currents. They are opposites. So what does that mean? Yep, it's a repulsive force. Those wires are actively trying to shove each other apart. Section 5, finding equilibrium distance.
So what if we flip the whole scenario on its head? What's genuinely cool about this formula is its algebraic flexibility. If we already know the exact force the wires are pushing or pulling with, we can totally reverse engineer the math to figure out exactly how far apart they must be.
Let's try it. Say we have wires carrying 8 amps and 12 amps in opposite directions, and we already know they're experiencing a repulsive force of 2.4 times 10 to the negative 4 newtons per meter. We literally just take our trusty equation and shuffle it around to isolate D. We plug in our known force and our currents, do the math, and it calculates out to 0.08 meters.
Let's convert that real quick to make it a bit more tangible. That is exactly 8 centimeters of separation. And honestly, this perfectly illustrates why mastering this one structural formula is so incredibly useful. You can use it to hunt down absolutely any missing piece of the puzzle in the system.
As we wrap up this explainer, I really want to leave you with this thought. We've been playing around with 5, 10, maybe 20 amps today, but think about major power grids. As currents surge into the thousands of amps, these invisible magnetic forces don't just add up, they multiply exponentially. So, at what point do engineers have to start massively reinforcing physical structures literally just to keep these cables from ripping themselves apart?
It's a wild reminder that these formulas on a screen, they absolutely dictate the heavy physical engineering of the world around us. Thanks for joining me on this explainer.